Welcome to the video lecture on solving trigonometric equations. A trigonometric equation is an equation that contains trigonometric functions. Sine 2x equals to 2 sine x cosine x, or 2 sine x plus 1 equals to 0 are examples of trig equations. Now the first one, hopefully you notice, is that double angle identity. So this is an identity, and it would be true for all x's. So no matter what x you plug in, the left side will always equal the right side. However, the second equation is what we call a conditional equation because it is only true for certain values of x. So the second one is true for only some x's. And if you think about what might work here, for example, sine of x, if sine of x takes on the value negative a half, 2 times negative a half is negative 1. Negative 1 plus 1 is equal to 0. So that would make it true. But what angle x makes sine of x become negative a half? Well, there's an infinite number of possibilities there, but something like 7 pi over 6 or 11 pi over 6 would work. So those are just some of the x's that might make this have a solution. Now, we have previously looked at ways of proving identities. We will now focus on finding solutions to conditional equations. Every trig equation eventually reduces to an equation of the form the trig function on the left, so you isolate that trig function, and everything else on the right side. So for example, if you have something fairly complicated, you're going to want to narrow it down so it turns into something like cosine of x on one side equals, say, a half, or tangent of x equals negative 1, or cosecant of x equals to 3. So you always want to get the trig function by itself on one side of the equation and a number on the other side of the equation. Now to solve an equation that is in this form, either we will remember our special values of our trig functions from our unit circle that we have memorized, or we may have to use the inverse function capabilities on our calculators. Now since each trig function is periodic, there will be an infinite number of solutions to almost every trig equation. For example, suppose we wanted to solve cosine of x equals to a half. So if you think about the graph of cosine of x, here it is, with all of its periods repeating over and over and over again. And if you look at 1/2, that's this horizontal line going across right through 0.5. So how many intersection points are there between that horizontal line at a height of 1/2 in cosine of x? Well, just within this window, we have 2, 4, 6, 8, 10 different solutions, but obviously you can see that there's going to be an infinite number of possibilities as we continue on. So what would we do to help simplify the matter here? What we often do is we just ask for what are the solutions in just the interval 0 to 2 pi. So if we think about that, in 0 to 2 pi, that would be this interval right here, we're talking about this solution and this solution. And these you should know in your head by that unit circle, because 1/2 is one of our nice trig values. So think about what angle makes cosine turn into a positive 1/2. And if we pull up our unit circle here, remember cosine is the x value. So here's positive 1/2 at pi over 3. In quadrant 1, we wouldn't want quadrant 2 or quadrant 3 because cosine is negative there, but in quadrant 4, 5 pi over 3 also gives a positive 1/2 for an answer. So just in the interval 0 to 2 pi, we could either have pi over 3 as a solution or 5 pi over 3. Now what we often do is once we find these solutions within one period length, 0 to 2 pi, we can easily use those to represent all of the solutions. So think about this. All of those angles in quadrant 1, which were equivalent to pi over 3, if we wanted to generalize what all of those angles would be equal to, we could add on a multiple of 2 pi. So this is how we write it. Pi over 3 plus 2k pi. Now remember, k here is an integer, so it can be negative. So if k is 0, then you're just going to get that pi over 3 solution. But if k is 1, then you'll get pi over 3 plus a 2 pi. If k is 2, you'll get pi over 3 plus 4 pi, or 2 revolutions. If k is negative, you'll get pi over 3 minus a 2 pi, and so forth. So you are getting all of those solutions in quadrant 1 that are equivalent to this pi over 3, but with 2 pi multiples either added or subtracted. Similarly, we can do the same thing for that 5 pi over 3 solution. So take that base angle 5 pi over 3, and then to get all of your infinite number of solutions, just add in a plus 2k pi. And remember, k is negative, so it will also get all those negative angles as well. For simplicity, we frequently restrict our intervals over which we report the solutions. So most of the time, you're just going to have to find it between 0 and 2 pi, but on some problems you will also have to find all of the solutions by doing exactly what I did here, adding in a 2k pi based on the period of the particular function that you're doing. So let's see an example. We want to solve the square root of 2 sine x minus 1 equals to 0. We want to first find all the solutions in the interval 0 to 2 pi, and we also want to find a representation for all of the solutions. So the first thing we're going to want to do whenever we're solving a trig equation is try to isolate that trig function if we can, which means get this sine of x by itself. So one way I can do that is I can add the 1 over to the other side, and then I can divide by this square root of 2 to get that coefficient out of the way. And 1 over root 2 is fine, or if you want to rationalize the denominator, that's square root of 2 over 2. Whoops. So hopefully you recognize that that root 2 over 2 is one of our nice values that we see in our unit circle. So this would be an example of one that you should be able to do by hand and not need a calculator for. Root 2 over 2 is that nice pi over 4 angle. So one solution would obviously be pi over 4, and remember that that's the angle that's in quadrant 1. But think about the other places where sine of x is also equal to a positive root 2 over 2. It's also positive in quadrant 2, so you need to know that pi over 4 angle in quadrant 2 as well, and it was 3 pi over 4. We wouldn't want 5 pi over 4 down here or 7 pi over 4 down here because those would give you negative sine values. Now these would be your two solutions in the interval 0 to 2 pi. So there's the first half of our answer. Now how would we write out the solutions for all of our infinite number of solutions? Well, that's where we're going to use that generalization. Because this is a sine function, and the sine function has a period of 2 pi, that's important, what we're going to do is take these two basic solutions that we got in one revolution, and we're just going to add in a 2k pi on the side. So pi over 4 plus 2k pi will get every possible angle that's equivalent to pi over 4 with all of its 2 pi multiples. And then if we take 3 pi over 4 and add 2k pi, then we'll get all the angles that are equivalent to 3 pi over 4 in quadrant 2. So here would be all of our generalizations. Okay, so let's try another example. Let's take a look at cotangent of 2x minus 1 equals to 0. Okay, so if we take a look at this next example, the first thing we're going to want to do is isolate that cotangent of 2x on one side and get the 1 on the other side. So I'm going to go ahead and add that 1 over to the other side. Now if you're comfortable working with cotangent and you want to solve directly from here, that's perfectly fine. Sometimes I find that students are a little bit more comfortable with just sine, cosine, and tangent. So if you prefer, you could change this to the reciprocal and rewrite it as 1 over tangent of 2x and then proceed from there. So I'm just going to show you this way in case that's your preference. Now when you get to this point, what you could do then is multiply that tangent of 2x over to the other side. And now we have this tangent function isolated. There's no coefficient in front of it, and there's nothing added or subtracted off to the side. So at this point, what we would want to do is we want to get at this x. And the only way to get at this x is to undo this tangent function. So what's going to undo a tangent? Well, an inverse tangent. So what we're going to do is take an inverse tangent of both sides, and that's going to cancel out that tangent, just giving me 2x. Now, think about what the value of the inverse tangent of 1 is. 1 is one of these nice values on our unit circle for tangent. So think about it for a moment. If we look at our unit circle, where on this unit circle is the tangent going to be 1? And remember, tangent is y over x. So the only way that's going to equal 1 is if the y and the x are the same. And that happens right here at pi over 4. So if I do root 2 over 2 divided by root 2 over 2, I'm going to get 1. So inverse tangent of 1 is pi over 4. Now that's just the answer in quadrant 1, but there are other places where tangent is positive 1, and that would also be in quadrant 3 as well. But I'm going to suggest to you here to think about the period of tangent before we proceed. And this is a kind of a tricky problem, and I'm going to show you why. Because when you're dealing with tangents or cotangents, you want to remember that the period of tangent is just pi. So what we're going to do is I'm going to suggest that you find the generalization of all of these solutions first before you immediately jump into trying to figure out what your solutions are between 0 and 2 pi. And I'll show you why it kind of makes it a little bit easier. So we found this pi over 4. It was just the answer in quadrant 1. And notice that this is not what x is, this is what 2x is. So here's what I'm going to suggest before we figure out what our first revolution solutions are, so what our solutions are between 0 and 2 pi, what I would suggest that you do instead is find your generalizations first. And the period here is important. So we're going to say that this 2x, and we haven't figured out what x is yet, I'm going to leave it 2x for a moment. Our solutions are going to be this base angle pi over 4 plus, normally we would do 2k pi, but this is where that period is important because we're dealing with the tangent function, and the period of tangent isn't 2 pi, the period of tangent is smaller, it's only pi. So what I'm going to add on to the side here is not a 2k pi, but just a k pi. And by doing that, that is going to not only give us that first quadrant angle at pi over 4, but it's also going to get us this one over here in quadrant 3, because if you take pi over 4 and you add pi to it, it's also going to give you that other positive value that we expect to see. So in this particular problem, because it was a tangent, I didn't need to list both pi over 4 and 5 pi over 4. I only needed to list the first one because when I add on that k pi, I'm going to be generating that third quadrant angle as well because of the smaller period. So that's one tricky part right there. Now the second tricky part is finishing this off for x, because this isn't what x is, this is what 2x is. So to finish solving for x, we're going to divide everything by 2. So I'm going to divide this by 2. Since this is already a fraction, just put that 2 in the denominator next to that 4. And for this piece, you also need to divide by 2, so that's going to get divided by 2 like that. And if we simplify, this gives me x equals pi over 8 plus k pi over 2. And this would be all of our solutions, all of those infinite solutions. Okay, this is going to generate all of those. So I would recommend finding that first, and then we're going to go down here and figure out what our solutions are in just the first revolution from 0 to 2 pi. So let's see how to figure that out. Now before I do that, what I would recommend is rewriting this slightly using a common denominator. We are going to be finding these solutions from 0 to 2 pi by plugging in various values of k. So we're going to let k be 0, we're going to let k be 1, and so forth. Now in order to be able to simplify what that answer is, it really helps us out if we have a common denominator down here. So since this pi over 8 has an 8 in the bottom, let's go ahead and make this k pi over 2 have an 8 in the bottom as well, and that would require multiplying by a 4 on top. So I'm just rewriting this as pi over 8 plus 4k pi over 8. And now what I'm going to do is I'm going to let k be 0 in this solution, in this generalization. If you let k be 0, then this whole fraction on the end goes away, and you're just going to get that basic angle that we started with, pi over 8. If I let k be 1, 4 times 1 is 4, so this is going to be that original pi over 8 plus a 4 pi over 8, and that becomes 5 pi over 8. So that's what we get when k is 1. Now let's let k be 2. If I let k be 2, then 4 times 2 is 8, so this becomes 8 pi over 8, plus that original pi over 8 makes this 9 pi over 8. If I let k be 3, 4 times 3 is 12, so now we're adding a 12 pi over 8 to the original pi over 8, so that gives me 13 pi over 8. Let's let k be 4. If I let k be 4, 4 times 4 is 16 pi, so that is going to make this 16 pi over 8 plus pi over 8, which would be 17 pi over 8. I'm going to stop you there, because how do you know when you're done? Well, think about what 2 pi is. 2 pi with a denominator of 8 is the same as 16 pi over 8. So when I plugged in k equals to 4 and I got 16 pi on top there, that means I'm taking 2 pi plus an additional pi over 8. That's outside of this interval. So this one is too big. We don't want to go that far. So my only solutions in the interval 0 to 2 pi are going to be these 4 solutions. And that's kind of a good thing to realize. When you have this coefficient in front of x, remember that compresses your period down by 2. So normally we would expect to have just 2 solutions, quadrant 1 and quadrant 4, but because we're doubling that period, now we actually get 2 times 2, or 4 solutions. So you're always going to get twice the number of answers that you would if this coefficient is 2. Okay? So just to recap here, we have up here in red the generalizations for all the infinite number of solutions to this equation, and then in blue we have just those 4 solutions that are in the interval 0 to 2 pi. And for these problems, especially the ones that have coefficients in front of that x, so that is that compression on that period, I always recommend figuring out what the generalization is first, and then letting k be 0, 1, 2, and so on until you get all of your solutions within that first rotation. And we'll do some more examples like this in a little while for more practice. Okay, let's take a look at tangent of x equals to 0.3. Now to solve this, we want to isolate our trig function, and this one already is, so we're all set to go. What makes this one a little bit different, however, is that we have a 0.3 over here, which is not one of our nice values on our unit circle. So in order to solve for x here, we're going to need to undo this tangent, which is what an inverse tangent is for, and we're going to need to use our calculator because 0.3 isn't one of our good angles, our good values. So we need to use our calculator to figure out what the inverse tangent of 0.3 is. So I'm going to pull out my calculator, and the first thing I'm going to do is I'm going to check my mode. And for these problems, typically we're in radians, so I'm going to switch this to radians. It's very rare that you'll be in degrees, but just check your problem and look for that degree symbol or the instructions if they really wanted you to use degrees. And we're just going to do an inverse tangent of 0.3. And here you need to remember what the restrictions are on the domain and range for inverse tangent. Remember that inverse tangents find you angles, so this 0.29 is an angle in radians, and it only gives you an angle that is between minus pi over 2 and pi over 2. So this answer, this angle, is something that's either in quadrant 1 or quadrant 4. If it's a positive 0.3 like we're working with, then that's going to have to be an angle in quadrant 1. If it had been a negative 0.3, then our answer would have been an angle in quadrant 4, and it would have been a negative 0.29 radians. So we just want to always keep in mind those restrictions on those inverse trig functions. So let's go ahead and write this down and see how we can finish off the problem from here. So we got that x was equal to 0.29 radians, and that is going to be, remember, in quadrant 1 somewhere, wherever that is, and we want to write out all of our solutions in the interval 0 to 2 pi and also all of our generalizations. So I'm just going to do my generalizations first. So all of my infinite number of solutions, and that's going to look like this base angle, and I'm only using the one value because this is a tangent again, and the period of tangent is pi. So by taking that 0.29 and adding on a k pi on the side, we're also going to get the answer that would exist in quadrant 3 as well. It would be redundant to find that answer and add a k pi onto it and list both of them, because then you're going to be repeating solutions. So we only need to find one of the answers in quadrant 1 and add in our k pi to get all possible values. So here's what our generalizations would be. To get our solutions between 0 and 2 pi, we're just going to let k be 0 in this generalization, which gives you that 0.29, and then we're going to let k be 1. So if k is 1, then that's just going to be whatever 0.29 plus pi is, and you can approximate that a little bit. That's about 3.43. Okay, so our two solutions between 0 and 2 pi would be 0.29 and 3.43. If I let k be 2, then this is going to be a 2 pi and I'll be outside of this interval, so I don't need to go any higher than k is equal to 1. Okay, let's try another example. Here we want the tangent of x minus pi over 2 equal to 1. So we want to isolate our trig function, and this one is, there's no constant added or subtracted off to the side. We do have this minus pi over 2, but it's in the parentheses next to our angle x. And there's no coefficient. So the only way to get at this x at this point would be to undo the tangent using an inverse tangent. So I'm going to get this angle part, this part right here, is now by itself because I'm canceling out that tangent by taking my inverse tangent. And this is a good value. Inverse tangent of 1, you should know that. Okay, that we've already done this already. That's that pi over 4, when the y and the x are both root 2 over 2. So I'm just going to give that one answer, that one angle in quadrant 1, and I'm going to generalize it by taking that pi over 4 and adding on our period times k. So k pi, since this is for tangent. Notice that I'm doing that before I finished solving for x here, and that's important. So to finish solving this for x, this one's a little bit different because notice to get x by itself, you have to undo this minus pi over 2, and that requires adding pi over 2 to both sides. And I'm going to add it to the constant pi over 4 that's in front there. So this will give me x by itself. What's pi over 4 plus pi over 2? Well, pi over 2 is like 2 pi over 4, so 2 pi over 4 plus pi over 4 is 3 pi over 4. So now we have just found out all of our generalizations. The next thing we want to do is find out which ones of these lie between 0 and 2 pi. So if I let k be 0, then this whole piece on the end goes away, and I just get 3 pi over 4. If I let k be 1, then I'm taking 3 pi over 4, and I'm trying to add pi to that. So let's get a common denominator. I'm going to turn that pi into 4 pi over 4, so 3 pi plus 4 pi would make this 7 pi over 4. And I can stop there because if I were to let k be 2, then I'm trying to add 2 pi on, and that's going to put me outside of this interval. So my only two solutions between 0 and 2 pi are 3 pi over 4 and 7 pi over 4. Okay, next example here. Secant of 5x equals to negative 2. So we want to isolate our trig function. It already is, but if you're not comfortable dealing with secant, you might want to change this to a cosine because secant is the reciprocal of a cosine. So that's what I'm going to do. I'm going to turn this into 1 over cosine of 5x equals to negative 2. And then I'm going to cross multiply that cosine over to the other side. And then I'm going to divide both sides by that coefficient negative 2 to try and isolate my cosine. Now right away from the very beginning, you see that 5 in front of the x. That means we have a horizontal compression going on with our period. So this is going to be similar to this one that we had up here, where you have twice as many, we had twice as many solutions as we would have anticipated. This time we're going to have 5 times as many solutions as we would anticipate because of that 5 in front of the x. So think about that a little bit in advance to kind of know what's coming up. Now we get to this point, negative a half equals cosine of 5x. To get at this x and the 5 as well, we have to undo this cosine. And the only way to do that is with an inverse cosine. So I'm going to take an inverse cosine of the negative 1/2, and this is a good value. So you have to think about your unit circle. Where would the inverse cosine be negative a half? Well, remember, inverse cosines are only going to give you solutions in quadrant 1, which this won't be because we have a negative 1/2, or quadrant 2, from 0 to pi. So what's the angle in quadrant 2 that has cosine equaling negative 1/2? Well, that's right here at 2 pi over 3. If you pull up the unit circle, you can see it right there. Now, if you were to do that on your calculator would only give you that one single value, 2 pi over 3. But we also know that cosine is also equal to negative a half at 4 pi over 3. So since this is one of these good values, you can kind of list out both of those at once. You don't have to be restricted to what your calculator would tell you. So in other words, this could be either 2 pi over 3, which is the quadrant 2 solution, or it could be 4 pi over 3, which is the quadrant 3 solution. Okay? So what I'm going to do, especially because of that 5 in there, is I'm going to list out my generalizations first. Now when it was tangents, I only listed one of these, not both, because the period of tangent was smaller. Here, remember, the period of cosine is 2 pi. So if I were to take 2 pi over 3 and add in a multiple of 2 pi to that, I'm not going to get this quadrant 3 solution. That's why you need to list both of these. When we did it with tangents and you added in just a k pi, you did get the other quadrant 3 solutions. So there was some redundancy there. So that's why we only used one base angle. Here we have to use both. So when I see this 5x and I write out my generalizations, I'm going to need to do the 2 pi over 3 solution plus 2k pi, and I'm also going to need to do the 4 pi over 3 solution plus 2k pi, since these will not overlap using various choices for k. Now remember, that's not what x is, that's what 5 times x is. So to finish solving this for x, we need to divide every single thing by 5. So where those 3's are, put a 5 next to it in the denominator. So this becomes 2 pi over 15 plus 2k pi over 5, or 4 pi over 15 plus 2k pi over 5. So there's our generalizations. To find your solutions in the interval 0 to 2 pi, before you do that, I would recommend changing these 5's to 15's and getting a common denominator. So I'm going to rewrite this as 2 pi over 15 plus, to get a 15 I have to multiply by 3, so this would be 6k pi, and this one would be 4 pi over 15 plus 6k pi over 15. So just get a common denominator. And now, to get the solutions from 0 to 2 pi, let's let k be 0. If k is 0, this goes away, and I just get 2 pi over 15 for this one. And if k is 0 here, I get 4 pi over 15. Now let's let k be 1. If k is 1 right here, I'm going to get a 6 pi on top. So 6 pi plus 2 pi is 8 pi over 15. If I let k be 1 here, I'm going to get 6 pi plus 4 pi is 10 pi over 15. Now I'm going to let k be 2. 6 times 2 is 12. 12 pi plus 2 pi is 14 pi over 15. And if I let k be 2 in this other one, 12 pi plus 4 pi is 16 pi over 15. Do I keep going? Yes, because remember, 2 pi, the denominator of 15, would be 30 pi over 15. So I need these numerators to get close to 30. So we have to keep going here. So let's let k be 3. If k is 3, 6 times 3 is 18. 18 plus 2 is going to make this 20 pi over 15. 6 times 3 is 18. 18 plus 4 is 22 pi over 15. Still getting closer to 30, but I'm not quite there yet. Let's let k be 4. K is 4. 6 times 4 is 24. 24 plus 2 is 26 pi over 15. If k is 4, I get 24 plus 4. That's 28 pi over 15. And that's probably where we're going to stop, but just to check, if you were to let k be 5, 6 times 5 would be that 30, and that's going to push you over 2 pi, so we don't want to go up to 5. So here's another way to help you remember how far to go. Count how many solutions we got. 2, 4, 6, 8, 10, which is exactly 5 times the original 2 that we anticipated. So you're always going to get whatever this coefficient is times however many you would initially find. So in this case 10, 5 times 2. Alright, so there's our solution for number 5. Okay, let's try another one. Sine of x equals to negative 0.8. So first thing I'm going to want to do is try to get this x value, and the sign is already isolated. Negative 0.8 is not one of these nice numbers on our unit circle, so to get at this x, you are going to need to use your calculator and do an inverse sine. So let's go ahead and punch that into our calculator and figure out what that is. So we're going to type in inverse, we're going to do inverse sine of negative 0.8. Hit enter. Now think about what this means. We get negative 0.927. Okay, let's go ahead and write that down, and then we'll think about what quadrant we're in and what this really reveals to us. So we got for x negative 0.927. Now remember, this was an inverse sine that we were doing. So this is an angle right here. This is radians. And if you think about where this would be located and where it's supposed to be located, remember, inverse sines, especially when you're doing them on your calculator, it is only going to give you values in quadrant 1 from 0 to pi, which this will not be because we were starting with a negative 0.8 and sine is positive in quadrant 1. Or it's going to give you a value between negative pi over 2 and 0 down here in quadrant 4. And that's what this is. So negative 0.927 is going this way down, and it's placing us down here in quadrant 4. So an inverse sine is only going to give you an angle between minus pi over 2 and pi over 2. So somewhere between quadrant 1 or quadrant 4. Now, is that the solutions that we want to give? Let's think about it a little bit. Are those the only places, is this angle right here, negative 0.927, the only solution that is going to give us the sine equaling negative 0.8? Is that the only place where sine takes on a negative 0.8 value? No, we know that there should also be one other solution because there's one other quadrant here where sine is negative, and namely that would be quadrant 3. So there's got to be some angle over here as well that's a solution that we need to figure it out. So let's think about how we can do this. And we also want to think about our solutions in the interval 0 to 2 pi, because negative 0.927 is not in that interval. That's a negative angle, and we're supposed to only be giving positive angles if we're going between 0 and 2 pi. So we also have an issue there as well. So let's see if we can figure out our solutions between 0 and 2 pi so that we can figure out what our base angles should be. So if this distance here is a negative 0.927, what would that be equivalent to going in a positive direction into quadrant 4? How would we figure out how much this is going around in the positive direction, but still being equivalent to 0.927? Well, hopefully you can see that if we went all the way around, that's 2 pi, and if I subtract that 0.927, that's going to get me to right here. So this angle going around here is 2 pi minus that 0.927, and that turns out to be about 5.36. So one solution over here in quadrant 4 is 5.36. That's what negative 0.927 is equivalent to, but as a positive angle. Okay, so we now know our quadrant 4 angle. What should the quadrant 3 angle be? How could we figure that out? So let's pick a different color here and see if we can visualize what this is. We know it's supposed to be over here, so how could we figure out what it is based on this negative 0.927? Well, from here to here is pi, and this amount right here is 0.927, but it's negative if I'm going down. So if we take that 0.927 and we add it to pi, add a positive 0.927, then we're taking this half circle plus this little arc length right here, and that should place me at the equivalent quadrant 3 angle that I'm looking for. So what is pi plus 0.927? It's about 4.07. So that's the quadrant 3 angle, and the 5.36 was the quadrant 4 angle. So this turns out to be about 4.07 radians. So you have to do a little bit of manipulating and thinking about, okay, should I be adding pi? Should I be subtracting pi? Should I be adding 2 pi's or minusing 2 pi's? What's it going to take to turn this answer from our calculator into a positive angle that's still equivalent to this and placing us in the right quadrants? And we wanted 2 different quadrants here. We wanted quadrant 3 and quadrant 4. So right away, now that we know these equivalent angles, we know our solutions in this interval 0 to 2 pi. The quadrant 3 solution is 4.07 approximately, and the quadrant 4 solution is 5.36. So that's that part of the answer. Now to get our generalizations, all we have to do is take those 2 basic angles, those are our base ones, and add in our period. And since this is a sine function, we're going to be adding in 2k pi. So there's all of the equivalent quadrant 3 angles, and 5.36 plus 2k pi would be all of the equivalent quadrant 4 angles. So this is my generalization, and this is my 0 to 2 pi solution. Okay. Now most trig equations are more complicated than the form trig x equals to a. So through the use of trig identities, algebraic manipulations, and equation solving properties, usually we can try to convert them into this isolated form. The given equation may be quadratic, radical, or fractional in nature, in which case we would solve it accordingly. And recall situations in which you might introduce extraneous solutions. One of the most common ways that you might introduce extra solutions that don't really check would be by squaring both sides. That's something that we often do when we're trying to solve radical equations. You hopefully remember that when you solve a radical and you square both sides, sometimes you get x's that don't actually work if you check them back into the original equation. And you will run across that sometimes in these problems as well. Another thing that you want to be on the lookout for are fractions. If you have a fraction, make sure that you check your solutions, because sometimes it might cause the denominator to equal 0. We never want the denominator to equal 0. So if a solution causes that to happen, then you have to disregard that as a possible solution. The equation may also involve multiple trig functions and or different arguments. So a subgoal in solving more complicated trig equations is to get an equation in a form involving a single trig function of a single number. So we're going to see lots of examples here that are starting to look a little bit more complicated. So let's start with this one. Cosecant squared x minus 4 equals to 0. So the first thing that we would probably try to do is isolate our trig function, just like we've been doing. And I could do that by adding that 4 over to the other side. Now, I personally prefer to rewrite this in terms of sines, because I don't like working with cosecants. So I'm going to change this to 1 over sine squared x is equal to 4, cross multiplying and dividing, or just taking a reciprocal of both sides, however you want to think about it. If you flip this over, you have to flip this side over as well. This should turn into sine squared of x equals to a 4th. In other words, if cosecant squared is 4, then the reciprocal sine squared x has to be the reciprocal 1/4. Okay? Now that we have it in terms of sines, what would we have to do to get rid of the square? Well, to get rid of a square, take a square root. Now remember that when you are the one taking a square root, you get two possible solutions, plus or minus. Don't forget both signs. And this reduces nicely to a 1/2. So what we're trying to think about here is what values of x, what angles x, if you were to take the sine of them, are going to give you positive 1/2 or minus 1/2. And this time on these problems, we're only looking for the solutions from 0 to 2 pi. So let's pull up our unit circle. Sine is the y value. So where are these y coordinates equal to positive or negative 1/2? Well, in quadrant 1, that's pi over 6. Quadrant 2, 5 pi over 6. Quadrant 3, 7 pi over 6 is when it hits a negative, and 11 pi over 6. So all of our 4 pi over 6 angles are going to work. So pi over 6, 5 pi over 6, 7 pi over 6, or 11 pi over 6. We did not square both sides, and we didn't have any fractions that might become 0, so this is our solution, and we don't have to worry about checking. Okay? Next one, 2 cosine squared x plus cosine x equals to 1. Now, this next example, you're going to do something here that you'll do quite often when you're solving these trig equations. So the first thing I want you to notice here is there is this cosine squared, but you also have this cosine x as well to the first power. If we are to subtract that 1 over to the left side, this is now going to take on the form of sort of like a trinomial. Imagine instead of having cosine x in there, instead call it y. This would be similar to 2y squared plus y minus 1 equals to 0. And what would you normally do if you were presented with an equation like that? Normally we would probably try factoring. If it's a quadratic trinomial, we would try reverse FOIL. So that's exactly what we're going to do on this one as well, but it's going to be just slightly more complicated because that cosine is in there. So to try reverse FOIL, we're going to set up two sets of parentheses, and I would need to have a 2 cosine x times a cosine x to get 2 cosine squared x. I would need a 1 and a 1 to get that 1, and in the middle I'm going to get a cosine x here and a 2 cosine x here. So what would my signs need to be so that I get a positive cosine as a result? Well, I would need this to be plus and this to be minus. So I need a minus here and I need a plus here. So cleaned up, factored, this looks like 2 cosine x minus 1 times cosine x plus 1 equals to 0. So the key to this problem is to factor. Now we're not done yet, but now that we have it factored, we can set each of these factors equal to 0. So I am going to add the 1 over to the other side, and I'm going to divide by 2, and that tells me that my solutions are going to be all the angles where cosine is equal to positive 1/2. And you only need to give solutions here between 0 and 2 pi. So if we look at our unit circle, cosine is the x value. Here's a positive 1/2, and then down here in quadrant 4 is a positive 1/2. So pi over 3 and 5 pi over 3 would be my two solutions for this first factor. So quadrant 1 and a quadrant 4 angle. Now we have to do this factor. So if we take our cosine of x plus 1, set it to 0, subtract that 1 over to the other side, where does cosine become negative 1? And hopefully you know that, that's right at pi. And there's only one place where that happens, between 0 and 2 pi. So my solution for that factor is just a pi. And since we only want our solutions between 0 and 2 pi, we don't have to worry about generalizing, and here would be our three solutions. Okay? Alright, let's try another example. Sine 2x sine x equals cosine x. So here we have not only sines and cosines mixed together, but we also have a double angle right here compared to single angles over here. So one of our important strategies is to try and make all of the angles be of the same type. So either make them all double angles, all 2 x's, or make them all x's. And then it's also usually nice to make these either all sines or all cosines. So let's see how we might go about doing that. Since I have this sine of 2x right here and the other two are just x's, it will probably be easiest to just try and change this sine of 2x into something with x's, and that's that double angle identity. So I'm just going to change this one using that identity to a 2 sine x cosine x. There will still be this sine x on the side and this cosine x on the right side. So if I clean this up just a little bit, sine x times a sine x will be a sine squared x. And what I want you to notice here is if I subtract that cosine over to the left side and get a 0, we're going to use that same strategy as above. We're going to factor. But it's not a trinomial this time. Instead, this time it's just going to be just a GCF type of factoring. Both this term and this term have a cosine in common, so we can factor these out. In parentheses, I would have 2 sine squared x minus 1. So here it wasn't actually even necessary to change these all to sines or cosines. You certainly could have. You could have changed this sine squared into a cosine by using an identity. But it's not necessary if you're able to factor, because we separated the two different types of trig functions, and now all I have to do is just let each one of these be 0. So let's take this first one and set it to 0. Where on the unit circle, on the interval 0 to 2 pi, including the 0 but not the 2 pi, where does cosine hit 0? Think about your unit circle. The x value needs to be 0, so that happens here at pi over 2 and also 3 pi over 2. So we're going to give both of those as our solution for x. Pi over 2 and 3 pi over 2. Now let's go to this second factor, Here we have a little bit more work to do. We're going to set it to 0, and I need to isolate that trig function, so I'm going to add 1, then I'm going to divide by 2, and because this is not sine x but sine squared x, to undo the square I need to take a square root of both sides. Don't forget your plus or minus symbol, and if you want you could think of this square root of 1/2 as 1 over root 2, or if you were to rationalize, root 2 over 2. That root 2 over 2 should strike a bell with you because that's that nice pi over 4 that we're used to seeing. And notice we're including all possible signs, positives and negatives. So we want not only quadrant 1 and 2 where sine is positive root 2 over 2, but also quadrant 3 and quadrant 4. So we should be getting 4 angles here between 0 and 2 pi. In quadrant 1, it's called pi over 4. Quadrant 2 is 3 pi over 4. Quadrant 3 is 5 pi over 4. And quadrant 4 is 7 pi over 4. So we want all 4 of those and our pi over 2 and 3 pi over 2 that we already got. Okay, next example, cosecant squared x equals to cotan x plus 1. So here we have a mixture of a cosecant and a cotangent. So this is one of those problems where it's probably a good idea to try to make the kind of trig function that you see in the problem consistently the same. So either turn these both into cosecants or both into cotangents. And in this case, it's easier to turn the cosecant squared into a cotangent because we have that Pythagorean identity for cosecant squared. Remember how it goes. Cosecant squared x is equal to 1 plus cotangent squared x. You need to have that memorized. So if we replace this cosecant squared x with this right-hand side, what we're doing is we're changing it so now everything is a cotangent. And we get a little bit lucky here because the 1's cancel out. So we get cotangent squared x equals to cotangent x. Now don't be tempted to divide by a cotangent here. You don't want to ever really divide by functions or x's because that potentially loses solutions. The better strategy is to subtract the cotangent over to the left side to get a 0 and factor it out. So don't divide, factor. So we're going to pull out a cotangent of x, and that's going to leave me with a cotangent of x minus 1. Once you have it set to 0 in a factored form, then all you have to do is set each factor to 0. So we need to know where cotangent of x is 0, and we need to know where cotangent of x minus 1 is 0, or in other words, cotangent of x is equal to 1. Now remember, cotangent is the reciprocal of tangent. So if tangent is y over x, cotangent is x over y on your unit circle. So let's think about our unit circle. In order for cotangent to be 0, we need x divided by y to equal 0, which is only going to happen when the x value is 0. So when is x, or cosine, 0? Well, that happens at pi over 2 and 3 pi over 2. So if we do x divided by y, both of those are going to be zeros. So this factor here has as its solution pi over 2 and 3 pi over 2. Now we need to know where cotangent is going to equal 1. So we need to know where x divided by y is going to equal 1. And that's only going to happen if x and y are the same. So that has to be, whoops, sorry about that, that has to be the pi over 4 angles. So we want, right here, pi over 4. And we want a positive one, so we want quadrant 1 and quadrant 3, where they're both negative. So pi over 4 and 5 pi over 4. So x is pi over 4 or 5 pi over 4 for this second factor. So there's our two solutions for that one. And all 4 of them together would be the solutions for the whole thing. Okay, next example. Here we have cosine of 2 theta plus 5 cosine theta plus 3 is equal to 0. The good news is they're all cosines. The bad news is they have different kinds of angles. We have a 2 theta here, but just a theta here. So one strategy is to try to make those angles match. And it's easier to get rid of a 2 theta than it is to turn a theta into a 2 theta. So what I would recommend is working with this cosine of 2 theta and using one of those double angle identities. Now cosine of 2 theta had several different options. The one I'm going to recommend using is the one that just had cosines in it. It was 2 cosine squared theta minus 1. I would use that because we don't want to try to introduce any sines into this equation when I only have cosines to begin with. That would make it more complicated. So instead, let's change this to 2 cosine squared theta minus 1. And now let's clean up our like terms and put it in descending order. So I'm going to put the 2 cosine squared theta first, then the 5 cosine theta, and a negative 1 plus a 3 becomes a positive 2. Factor, factor, factor. That's a huge strategy in these trig equations. Almost all of them are going to involve some kind of factoring. This is like a trinomial because you've got that square and then you've got that middle term which has degree 1. So try reverse FOIL. 2 sets of parentheses. I need a 2 cosine theta times a cosine theta to be 2 cosine squared theta. And I'm going to need a 1 and a 2 to get 2, but you want to put the 2 here and the 1 here, so you'll get 1 cosine theta and a 4 cosine theta to get you that 5. I need them both to be plus so that you'll get a plus 5 in the middle. So now we have it factored. We're going to set each one to 0, and then we'll have our solutions. So I'm going to set this first factor to 0. Let's go ahead and subtract the 1 and divide by 2. And then we need to think about our unit circle. Where on the unit circle in all of our quadrants is cosine going to hit negative 1/2? So negative 1/2 for the x value. So that happens right here in quadrant 2 at 2 pi over 3 and also in quadrant 3 at 4 pi over 3. So 2 pi over 3 and 4 pi over 3. If you don't know that unit circle yet, you really need to know it in order to make these trig equations go much smoother. For the second factor, we're going to set this to 0, and we're going to subtract that 2 over to the other side. And negative 2 is not one of our nice values on our unit circle, and it should also kind of give you a pause here because you need to think about cosine. What's the largest or smallest value that cosine ever takes on? Well, since it's a unit circle with a radius of 1, the biggest that cosine can get is positive 1, and the smallest that cosine can get is negative 1. You can also think about that using the graph of cosine. It never goes beyond negative 1 or 1. So where does cosine hit negative 2? That's impossible. That's just too small. So the only solutions here would be 2 pi over 3 and 4 pi over 3. Okay, on this next example, we're in good shape in that all of our trig functions here are tangents, but we've got various different powers. So when we look at this, what you want to notice is that we have 1, 2, 3, 4 different terms. The powers are decreasing, and what it looks like, hopefully you can kind of catch on, is that if we have 4 terms, one thing that we often try, especially in our factoring strategies, is factoring by grouping, and this has very good potential for that. If we group together these two, they both have a GCF that I can pull out. I can pull out a 5 and a tangent squared x. What that would leave me with would be a tangent x from this first factor, and all of this is gone, so I'll just have a minus 1. Now the way factoring by grouping works is then you would group these last two terms together and hope that once you pull out something from those two, what's left in these parentheses matches what's in these parentheses exactly. And what I have left is almost the same already, but what's different are the signs. The signs up here are backwards from what they should be down here. So all I have to do to fix that is pull out a negative. If I pull out that minus, then I'm going to be left with a positive tangent of x, and I would need a minus 1 inside the parentheses so that if I were to redistribute the negative, I'd get back my plus. So now this is really good because these two things match. Therefore, I can pull out the tangent x minus 1, and then in parentheses, now that these two things are gone, I would have 5 tangent squared x minus 1 left over. So now it's in factored form, which means I can set this factor to 0, add the 1 to the other side, and then we're asking the question here, what does x need to be so that the tangent of it will give me back 1? And we've been doing this quite a bit today. We would need that y and the x value of our points on our unit circle to be the same. So it needs to be those root 2 over 2's, which gives you an angle of pi over 4. Now what quadrant is tangent positive in? Because we want positive 1. So if you think about your unit circle, pi over 4 is here in quadrant 1. Tangent is also positive in quadrant 3. So what's the corresponding pi over 4 angle in quadrant 3? That would be 5 pi over 4. And we just want one revolution. So between 0 and 2 pi, those are my two solutions. Okay? Now we go to this factor. Now this one's a little bit more complicated. We have 5 tangent squared x minus 1 equals to 0. We're going to want to add that 1 over to the other side, divide by 5. We're trying to isolate that tangent as much as we can. Now once we get to this point, this is what tangent squared equals. So how do we figure out what its tangent is? We're going to need to take a square root of both sides. Now when you take a square root, remember you have to have that plus or minus symbol. So this is asking for where does the tangent of x equal positive square root of 1/5 or negative square root of 1/5. And that is not going to be one of those nice values on our unit circle. So we will need to use a calculator. And because we're looking at both signs, positive and negative, you're going to want to consider the inverse tangent of each case. So the plus case or the inverse tangent of the minus case. So let's pull out the calculator and see what decimals we get for these values. So we're going to do the inverse tangent of 1 divided by the square root of 5, and we get 0.4205. And then if we do this again for the negative case, we should get exactly the same decimal, but it's opposite because it's that fourth quadrant angle. Yep, so we get 0.4205 and negative 0.4205. So let's write these down and then we'll go from there to see what our final answers should be. So our x's were positive and negative 0.4205, or I'll just round it off to 0.42 for right now. So let's visualize what we have on our unit circle. Now 0.42, remember that's an angle in radians, so somewhere over here is this 0.42 angle, and then negative 0.42 would be down here. Are those two answers our only two solutions? No, because remember we have this plus or minus sign, so there are two quadrants between 0 and 2 pi where tangent is positive, quadrant 1 and quadrant 3, and there's two places where tangent is negative, so down here in quadrant 4, but also up here in quadrant 2. So we need to figure out what this, and this is equal to within the interval 0 to 2 pi. So obviously the 0.42 is fine. That is within 0 to 2 pi, and that's our quadrant 1 solution. So we already know one of our answers. But the negative 0.42 isn't going to work, even though it's quadrant 4, because it's a negative value and it doesn't lie within this interval. So we're going to need to use this positive 0.42 somehow and manipulate how we get these other three angles that we know should be our solutions. So let's think about how we could come up with this quadrant 2 angle. If we know that this much right here is 0.42, then by symmetry this much over here should be 0.42 as well. But we want to get this angle, which should be all the way from the positive x-axis to this little line right here. So how can we measure this whole distance here? Well, it's got to be all the way from here down, which is pi, minus this little tiny reference angle right here, which we know is that 0.42. So to get the quadrant 2 angle, we're taking pi all the way down minus that 0.42. And if you do that on your calculator, you get 2.72. So that's the quadrant 2 angle. We know that the 0.42 is the quadrant 1 angle. Now let's work on trying to figure out what the quadrant 3 angle should be. So if we look at our picture here again, let me clear off some values here a little bit. Let's go back and visualize what we know. We know this much right here is 0.42, and we're trying to figure out what this is over here. So the distance along the circle right here is 0.42. That should correspond to this same distance down from pi that we want to go. So to get from the positive x-axis all the way down to here, we're going to need to go from here to here, which is pi, plus this extra little 0.42. So this time, instead of pi minus 0.42, we want pi plus 0.42. And on a calculator, when you punch that in, you get about 3.56. So there's our quadrant 3 angle. Okay, finally we need to get our quadrant 4 angle. So if we draw our circle here again, here's that 0.42, and down here is where we're trying to get. So again, by symmetry, this distance here is 0.42, so would this distance right here be as well. So to get this angle, we're going to need to start at the positive x-axis and loop all the way around and go to here. So you can see, hopefully, that that's all the way around the circle, which would be 2 pi radians, minus this little distance here, which we know is that 0.42. So to get our quadrant 4 angle, it's 2 pi minus 0.42. So our final decimal, if you punch that in your calculator, that's about 5.86. So these decimal values, they're kind of tricky. You're going to use your calculator to kind of get your starting point, usually your quadrant 1 type angle, and then you need to use that and either add in a pi, subtract in a pi, or add in or subtract a 2 pi in order to figure out what those other corresponding quadrant angles are going to be. Alright, the next example here is a little bit different. We have tangent of x over 2 minus sine of x equals to 0. And we have a couple of issues here. First of all, we've got two different kinds of trig functions, tangent and sine, and we also have two different kinds of angles. So usually when you have like an x over 2 like this or a 2x, we pull out some of those identities, and this would be that half angle identity. So that's probably where I would start on a problem like this, because it gives me a place to kind of go from. Now when you think about the half angle identity for tangent of x over 2, there are a couple different versions of this. My personal preference is to use the one that looks like sine of x over 1 plus cosine x. But you could also use 1 minus cosine x over sine x. Both of those are acceptable. They would give you slightly different work, but probably the same amount of steps to get to your final solution. So use whichever one you like best. So what I'm going to do is replace this tangent of x over 2 with sine x over 1 plus cosine x, and we want to subtract sine x from that and set it to 0. Now when I look at this, I have a fraction minus my sine of x. So the only way I'm going to be able to simplify that is to get a common denominator. So my common denominator wants to be that 1 plus cosine x. This first fraction already has that, so my numerator isn't going to change. It's going to stay sine of x. The second fraction here doesn't have this 1 plus cosine of x in the bottom. It's just got a factor of 1 down there. So I would have to multiply top and bottom by this 1 plus cosine x. So my new numerator would be the sine of x that I already had times this 1 plus cosine x in parentheses. Okay, now on top I can simplify by distributing. So let's distribute our negative and our sine of x across. I'll get minus sine of x minus sine of x cosine x. And that means on the top, my signs are going to cancel. So we have negative sine x cosine x all over 1 plus cosine x equals to 0. Now you have a couple options how you can think about this next step. If you want, you can just think about taking this denominator and cross-multiplying it over to the other side. And since it's getting multiplied by 0, it's just going to stay 0, and all we would get is that numerator. Another way to think about this is this left side is a fraction, and the only way a fraction can equal 0 is if the numerator is 0. So same result, whichever way you think about it. Now this negative is like a negative 1, so if you don't like that being there, you can divide through by that negative 1 as well. So really all we're dealing with is sine of x cosine of x equals to 0. So there's lots of ways to proceed from here, but probably the most straightforward way would be to realize that we've taken this difference up here and we've turned it into a product. Now we have a sine of x times a cosine of x, and we want that product to equal 0. And the only way a product can equal 0 is if each factor is equal to 0. So all we have to do from here is take that sine of x and set it to 0, and this cosine of x and set it to 0, and find out what our solutions are. So think about your unit circle. On your unit circle, sine is the y coordinate. Where is y equal to 0 on the unit circle? Here and here. So that's going to be 0 and pi. It would also be 2 pi, but on our interval, we have an open endpoint at 2 pi, so we're not including 2 pi itself. Okay, now let's think about cosine of x. Cosine is the x coordinate. So where on our unit circle is the x coordinate equal to 0? That would be here and here. So that's going to be at pi over 2 or 3 pi over 2. Now I want to warn you, when you have these solutions, let me rewrite them up here. 0, pi, pi over 2, and 3 pi over 2. Remember that the original problem that we had did involve a tangent, and tangent does have places where it could become undefined. So you do want to check your solutions whenever there's fractions involved. And we got fractions when we were solving this problem over here. So that's kind of a clue that you do want to check your answers. You can check them back into any of these steps here, or you can check them back into the original equation. I'm going to check it back into the original just because this to me is a little bit simpler to plug things into. Now really, we only need to worry about the tangent piece because we know that sine is defined at 0, pi, pi over 2, and 3 pi over 2. So this is okay. We don't have to worry about that ever becoming undefined. When we're dealing with fractions, you only need to look at the part that might become undefined, which in this case is this tangent part. So let's check each of our 4 solutions into this tangent. So if I take 0 and I plug in 0 for this x, this would become tangent of 0 over 2, which is just tangent of 0. And 0 has what value for tangent? If you look at your unit circle, it has a y value of 0 and an x value of 1, and tangent is y over x. So 0 over 1 is just 0. So that's defined. So this is okay. We don't have to worry about that becoming undefined. We're not really checking anything other than, is it in the domain of tangent? Let's take a look at pi. Remember, we're taking this pi and we're plugging it in for this x right here. So when I plug in pi, it turns into a pi over 2. So let's look at our unit circle. At pi over 2, we're at the ordered pair 0, 1. When I do y divided by x, it becomes 1 divided by 0, which is undefined. And that corresponds to that vertical asymptote that we see on the graph of tangent. So pi over 2 is undefined, which means it's not a valid solution. We can't use it because if I were to plug it back into the original equation, it's not going to be true, it's not going to exist. So we have to cross that one off. If we take a look at pi over 2 for x, remember it's going right here. What happens when you take pi over 2 and you divide it by 2? It just turns into a pi over 4. Is the tangent of pi over 4 defined? Yeah, we know that that's 1. So that's okay. We're allowed to use that because that exists. And then finally, if I try 3 pi over 2, What does 3 pi over 2 divided by 2 become? Well, that becomes 3 pi over 4. And tangent of 3 pi over 4 is equal to -1. That's the same as pi over 4, but it's in quadrant 2. So that exists as well. So notice I'm not really checking to see is the equation true. I mean, it still will be if we did the full plug-in of all of our x's into everything in the original equation. What I'm really just worried about in this particular problem is the fact that tangent does occasionally become undefined. So you have to check your final solutions and make sure that they are within the domain of this equation. So since pi made the tangent of pi over 2 become undefined, we can't use it as a solution. So be careful with fractions. If you have fractions, check your domains. Okay, the next example here, cosine of 5x minus cosine of 7x is equal to 0. Now this one's a little bit difficult to work with initially because we have two cosines, which is great, but we have two different angles. We've got a 5x and a 7x. Now in the past, when we've had different angles, they were usually either a 2x or an x over 2, which then implied that we could use either a double angle identity or a half angle identity. But we don't have any identities for 5x or 7x, so we're kind of stumped at this point. And so this is where this hint comes into play. The only really good way to deal with this problem is to turn it into, instead of being this difference right here, turning it into a product and using one of those sum to product identities. Now these are not identities that I would expect you to have memorized. I would give it to you on a test. And the one that this one looks similar to is cosine of an angle, where our angle here is this 5x, that's going to be our u, minus cosine of another angle, so this is going to be my v. So I have the difference of two different cosines. What this turns into, according to this identity, is minus 2 sine of u plus v all over 2 times sine of u minus v all over 2. So we're going to apply this identity to this left-hand side. So it's going to become -2 sine of the u plus the v all over 2 times the sine of the u minus the v all over 2, and we want that to equal 0. So if we simplify, 5x plus 7x is 12x, dividing that by 2 gives you 6x. 5x minus 7x is -2x, dividing that by 2 gives you a minus x. Now a couple of simplification things here. We know that sine is an odd function, which means if you have a negative inside next to that x, you can pull that negative out. So this negative right here is going to cancel out this negative here, and we're just going to be left with a positive 2. Now what about that 2? Well, it's just a constant, so we can divide both sides by 2 to clear it out of the way. So now what we have, instead of having a difference of two cosine functions with two different angles, we've turned this into a product of two different sines. And yes, they do have two different angles, but because it's a product set equal to 0, we can now just set each of these factors equal to 0. So it's okay that their angles don't match, because we can go ahead and set each of these to 0 automatically. Now let's do the easier case first. Let's deal with the sine of x equaling 0. Where does sine hit 0? And sine is that y coordinate. So that's going to be here at 0 or here at pi. So those are two solutions that I have so far. Now this one is going to be a little bit more complicated. Let me pull it over here so we have more room. We already know where sine hits 0. So now what we need to realize, remember this has a coefficient in front of that x. So that's going to change that period of this sine function and make it a horizontal compression. So what we're going to need to be careful of here whenever we have these coefficients in front of 6's is the fact that you're going to be generating a lot more solutions. So this is how I like to do this. I'm going to take this angle here, whatever it happens to be, and in this problem it's that 6x, and I'm going to set it equal to whatever the inverse sine of 0 is. And we already know what the inverse sine of 0 is. It's either 0 or it's pi within one revolution. If we're talking between 0 and 2 pi, those would be my two base angles. Now because sine has a period of 2 pi, I'm going to get my generalizations from this. And we haven't done this in a while, but on these problems where there's that coefficient in front of x, I always like to write out my generalizations first and then figure out which angles I need that lie between 0 and 2 pi. So we're going to take this base angle of 0, and because the period of sine is 2 pi, I'm going to write plus 2k pi. And then I'm going to take my other base angle pi and I'm going to add 2k pi. And then to solve for just x, we need to divide every single piece here by 6. So this becomes x equals, this just goes to 0, and we get, if I reduce here, k pi over 3. And then this one is pi over 6 plus 2k pi over 6, or k pi over 3. I'm going to leave it as 2k pi over 6 so that I maintain that common denominator, which is going to help me in my next step. So these would be your generalizations. But in this particular problem, we really just wanted to know the solutions in the interval 0 to 2 pi. So to figure those out, now what I do is I choose my different choices for k. Let's start by letting k be 0. If k is 0 in this first answer, then this whole thing goes to 0. If k is 0 here, all of this goes to 0 and I just get that pi over 6. Now let's let k be 1. If I let k be 1 here, I get pi over 3. If I let k be 1 here, I get 2 pi plus pi gives me 3 pi over 6, or that reduces to pi over 2. If I let k be 2, this becomes 2 pi over 3. And if I let k be 2 over here, 2 times 2 is 4, so I get 4 pi plus pi is 5 pi over 6. If I let k be 3, 3 pi over 3 reduces to pi. And if I plug in 3 here, I get 2 times 3 is 6, plus 1 is 7, so this will be 7 pi over 6. If I let k be 4, I get 4 pi over 3. And here, 2 times 4 is 8, plus 1 is 9, so this would be 9 pi over 6, which reduces to 3 pi over 2. And if I let k be 5, I get 5 pi over 3. Or 2 times 5 is 10, plus 1 is 11 pi over 6. And that's where you can stop. These are going to be my solutions. If I were to let k be 6, then you'd get 6 pi over 3, which is 2 pi, and that's outside of our interval that we're looking at. Notice how many solutions we had. You get 12 of them down here, and that's because you're getting 6 times 2. So that's what that number in front of that x does. It multiplies the number of solutions you normally would have, which is normally 2 for sine, and it multiplies it by that 6. The other two solutions we got from that other factor, remember that 0 and pi, they happen to be in here already, so they kind of got repeated. So this whole list is my solution set. Okay, next example here. Cosine x, cosine 2x plus sine x, sine 2x. Now on this one we have sines and cosines, we have double angles here, so you have lots of options. One thing you might be tempted to do is to use a double angle identity for cosine and a double angle identity for sine, substitute those in, and it will work for you. However, it's going to take you quite a few steps probably to make it work. What I want you to notice is the way that this left side is set up. This has the look of cosine alpha, cosine beta, plus sine alpha, sine beta, where this x is our alpha and this 2x is our beta. Now if you happen to notice that pattern, then you should know, because you're supposed to have this memorized, that this left side is the expansion of our difference formula for cosine. In other words, this is the formula we get when we do cosine of the first angle alpha minus the second angle beta. You need to have opposite signs, so if this is minus, this is plus. So noticing that means we can turn this whole left side into this difference, a single cosine of our alpha, which is our x, minus our beta, which is our 2x. And that's good because x minus 2x is just negative x, And that's good because cosine is even, so this negative gets absorbed and disappears. So this is just cosine of x on the left side. So without a whole lot of work, we were able to turn this left side into just cosine x. And like I said, you probably could get that by using those double angle identities, but this is a much faster route to getting to that point. So now to finish solving the equation, we need to solve for x. And unfortunately, -1/5 is not one of those nice values on our unit circle, so we will need to use our calculator and take an inverse cosine of -1/5. Remember here in advance that for an inverse cosine on your calculator, if the number that you're taking the inverse cosine of is positive, you're going to get an angle in the first quadrant between 0 and pi/2. If the if the number that you're trying to take the inverse cosine of is negative, you're going to get an angle over here in quadrant 2, because the domain and range restrictions on inverse cosine say that you're always going to get an angle between 0 and pi only. So this is negative, so we should predict that we're going to get something over here in quadrant 2. So if we pull up the calculator, we'll be able to figure that out. Now I'm going to skip that step temporarily and tell you what the decimal is. We'll get that calculator up in a moment. But if we punch it in, you'll see that you get 1.77 radians. And it should be somewhere over here, and I don't know exactly where it lies, but it's somewhere over there in quadrant 2. So just to verify that, in case you don't believe me, we pull up our calculator and we do an inverse cosine of -1/5. We get 1.77. Okay. So we have this angle 1.77. Notice that it's in quadrant 2. Is that going to be the only solution between 0 and 2 pi where cosine hits -1/5? No, it shouldn't be. We know that cosine takes on that negative value in quadrant 2, but it should also hit that same value in quadrant 3 as well, somewhere down here, because cosine is negative in quadrants 2 and 3. So we know what one of our answers is. We know that x is 1.77. That's the quadrant 2 solution. But what's the quadrant 3 solution? So this is where we're going to have to be a little bit careful. It's probably going to involve some adding and subtracting of pi's or something like that. So let's visualize what we've got going on. This much right here is that 1.77. So how can I use that to figure out what this mark down here is going to be? By symmetry, this amount down here would be -1.77, going in the clockwise direction. So we can use that to our benefit, because to get to this point here, we can do all the way to 2 pi, and then we can subtract off this 1.77, so take away this amount from the 2 pi, and that should land us right where that little blue mark is. So the way that I'm going to get this quadrant 3 angle is I'm going to take 2 pi minus 1.77. And we get 4.51. So our quadrant 3 solution is 4.511. And there are 2 solutions in one revolution from 0 to 2 pi. Okay, the next example here is a little bit different. When we look at this, we have square root of 3 sine theta plus cosine theta equals to 1. Let's think about some of the strategies that we've used so far today. If we had some squares involved, we could either use some identities or we could try factoring. I don't have any squares here at all. If we had any half angles or double angles, we could use some of those identities. We don't have any of those either. So we're kind of stuck. There doesn't seem to be much that we can do with this problem. If you have never seen this problem before, you probably wouldn't think to do what we're actually going to do. But with experience and practice, you'll know to try this strategy when you kind of get stuck. So here's what we're going to do. We're going to square both sides. We're going to introduce some squares into this equation so that we can use some of the identities that we know. Because right now, there's no identities that I can really apply that are going to make this doable. Now, before you square both sides, I would strongly recommend that you separate the sine and the cosine and get them on opposite sides of the equals. So I'm going to subtract that cosine over to the right side. The reason for moving it over is it's just going to make squaring both sides much simpler, and it'll help avoid mistakes like forgetting to FOIL correctly. So once I move that cosine over, what we're going to do is we're going to square both sides. When I square the root 3, it just becomes a 3. When I square the sine, it becomes sine squared. On the right side, please remember to FOIL. You will get a middle term over here. You'll get that 1 squared, which is 1. You'll get a minus cosine theta and another minus cosine theta, which becomes minus 2 cosine theta. And then we'll get a plus cosine squared theta. So now we have some squares involved. So that means we can try to use some of our identities, like our Pythagorean identities. Notice on the right side we have all cosines. On the left we just have the 1 sine squared. So your strategy at this point is to use the Pythagorean identity that's going to take this sine squared and turn it into a cosine squared so that we have one consistent trig function throughout this whole equation. So I'm going to replace this sine squared with 1 minus cosine squared theta. That's just that Pythagorean identity that we know. And then I'm going to distribute my 3 across. And then I'm going to combine some like terms. I'm going to start moving things around. Let's add this 3 cosine squared theta over to the right side. And while we're at it, let's subtract our 3. So you're going to get a 0 on that left side. You'll get a minus 2 cosine theta, and a plus 4 cosine squared theta. Now, if you are like me, it kind of bothers me to have it in this order. I like to have it in descending order. So I'm going to just switch the terms around to put the cosine squared term first, then our middle term, and then that minus 2. What we're hoping here is that by getting all the cosines into play here, hopefully we are left with something that we can factor. And this should. It has the look of a trinomial. Please note that all of these coefficients are divisible by 2. So you can pull out a GCF of a 2 first, and it'll just make that factoring step go even simpler when you're trying to do that reverse FOIL. So I like to pull out my GCF first, and then break this down into our 2 sets of parentheses. I need a 2 cosine theta and a cosine theta to get 2 cosine squared. I need a 1 and a 1 to get my 1. And since I want my middle term to be minus, I'm going to need this to be minus, so I'll have a negative 2 cosine theta, and this needs to be plus so that I have a plus cosine theta, and they'll add together to a minus 1. Great, now we have it factored. We can set each factor to 0. Now notice this 2 is just a constant. It doesn't have a theta, so it's not going to contribute any solutions. You don't need to set it to 0 because it never will equal 0. Only this factor or this factor with the thetas will equal 0. So let's set this one to 0. I'm going to subtract the 1 and divide by 2. So we're asking ourselves, where does cosine equal to negative a half? And if you pull up the unit circle, that's right here at 2 pi over 3, and in quadrant 3, right here at 4 pi over 3. So this is going to have solutions of 2 pi over 3 or 4 pi over 3. Now if we look at this factor and set it to 0, add the 1 to the other side, where does cosine hit 1? Well, that's either at 0 or 2 pi, but we're not including 2 pi in our interval. We're just going up to it but not including it. So 0 is also a solution as well. Now, back up. What did we do to get these solutions? The only thing we could do to make this work was to square both sides. But you want to remember that whenever you square both sides, this could potentially lead to extraneous solutions. So you have to check your answers. This is just like what we have to do whenever we're solving radical equations. When you solve both sides, or when you square both sides, sometimes you get solutions that don't make the radicals true anymore. So you have to check. So we want to go back to our original equation, always go back to the original one, and we're going to substitute in each of these three values and see if they really work. So let's try 2 pi over 3 first. We're going to get square root of 3 times the sine of 2 pi over 3. Now remember, sine of 2 pi over 3, that's this y coordinate, so that's square root of 3 over 2. And then we want to add to that the cosine of 2 pi over 3, which was that negative 1/2, that x coordinate. Root 3 times root 3 is 3, so this becomes 3 halves. Minus a half gives you 2 halves, which is 1, and that's what we wanted it to equal. So that one works. This is a valid solution. Okay, let's try 4 pi over 3. Now when you plug in 4 pi over 3, you get square root of 3 times the sine of 4 pi over 3. Now 4 pi over 3 is in quadrant 3, so the sine value is still going to be a root 3 over 2, but in quadrant 3 sine is negative. So now it's a negative root 3 over 2. Cosine of 4 pi over 3 is still negative 1/2. So when we do this, we get a root 3 times a negative root 3, so now this is a minus 3 halves minus 1/2, which is negative 2 halves, which is negative 1. Excuse me, negative 4 halves, which is negative 2, but it's not 1. That's what matters. So we don't get a true solution here. It doesn't check out when we substitute it back in. So this one we have to cross off our list. Finally, let's try 0. If we plug in 0 into our equation, we're going to get root 3 times the sine of 0, and the sine of 0 is still 0. And then we want to add to that the cosine of 0, and the cosine of 0 is 1. So this goes to 0, and we get just 1 equals 1, and that's what we wanted. So this is also a valid solution. So just remember, when all else fails on your equations, if you're not sure what to do, if you're totally stuck, sometimes squaring both sides helps. It gets those squares involved so that you can start using some of your identities. However, when you square both sides, you sometimes create extraneous solutions, so you always have to check each of your answers back into the original equation to make sure that they really are true. And if they don't check out, just cross them off and don't include them in your final solutions. Okay, finally, we're up to our last equation. This one is very different than all the rest that we've done today because it's comparing a sine of x and setting it equal to an ln of x, a logarithm. So here we are setting two totally different types of equations equal to each other. When that happens, you are almost always going to have to do it graphically. There's very few cases where you can actually do this algebraically. We just don't have any strategies on how to deal with this. There's no identities that we can use, there's no simplifying, there's no factoring, squaring's not going to help. We're pretty much stuck and there's nothing we can do about it. So when you're presented with an equation that's comparing trig functions to polynomials or trig functions to exponentials or logs, then pull out the calculator and do it graphically. Now you have two choices for how to do this graphically. One option is to let your y1 be the left side of the equation, sine x, and let y2 be the right side of your equation, that ln of x. Then you would graph these simultaneously. So this would look something like this for sine, and then ln of x looks something like this. And you'd be looking for this intersection point. The other option, and this is usually the way that I like to do it, is to take this equation and subtract that ln of x over to the other side to get a 0. And then in your y1, you just let y1 be that whole left side of your equation. And instead of looking for intersection points, now we're looking for zeros. So I'm going to show you this method, okay? So what we're going to do is pull up the calculator, And whenever you're graphing any kind of trig function, you always want to be in radian mode. So just double check that. We are still in radian mode. And then in my y1, we're going to plug in sine of x minus ln of x. And I'm just going to go with a standard window because I'm not quite sure yet what I want this to look like. So we'll just go with the standard window. Oops, I must have typed something in wrong. Let's double check. Oh, I had an extra parentheses in there, sorry. So let's hit graph. And here's what it looks like so far. Now you can hopefully see that over here it looks like I've got a 0, but we're not quite sure what's happening to the right. So you might want to expand your window a little bit to the right and make it a little larger. Notice that I don't have any graph over here to the left for these negative x's, and that's because of the domain of ln. ln, you're only allowed to plug in positive x values. So this is not going to have any points over here for these negatives. So let's just get rid of those altogether. So let's go to our window. And I'm going to start it at 0 since I don't need any negative x's. And let's just boost this x max up to 25 maybe, and just kind of see what we're dealing with. We don't want to miss any zeros, so this is just trying to verify for us that we're not going to miss any. So here's our graph, and hopefully this is convincing for you because you can see this pattern. You see almost that wave motion, but the waves are getting lower and lower each time. So to me that's pretty convincing that this graph is not going to suddenly turn back around and cross that x-axis. So the only 0 that I see is right over here. So I'm convinced that there's only one, and I'm going to go to my calc command. Number 2 is 0. And we just need to move that cursor over to our 0 where we think it is. Place it over that 0. And for my left bound, just do 1 or 2 clicks to the left. Hit enter. Then put your cursor back over the 0. And for the right bound, do 1 or 2 clicks to the right. Hit enter. And then go back to that 0 for your guess. And we get 2.219. So our solution is 2.219 for x. And this would be radians. This is an angle. So that's the value of x where sine and ln cross. So that would be this x value right here. Okay? Alright, we just finished our lecture on solving trig equations. This is a complicated lecture. There's a lot of different strategies to think about and a lot of different things that you have to worry about. So practice, practice, practice. It does take a lot of experience to kind of know what strategies to use. So please be prepared to be a little frustrated at the beginning, but the more problems you do, the better you'll get at them and you'll kind of know what to expect. So good luck. This concludes our lecture on solving trigonometric equations.